In the last few videos, we've been dealing with the second law of thermodynamics in a few different forms. Today we will see perhaps the most well-known version of the second law, the one dealing with entropy. So far, we have really only applied the second law of thermodynamics to cycles, but what about processes that are not cyclic? In these cases, it is easier to deal with the second law in terms of entropy. So the big question now is, what exactly is entropy? But the answer is not easy, so bear with me. Entropy is a measure of randomness on a molecular scale, which again is not an easy thing to define. But we can make some general statements without getting into too many technical details. Substances in the gas state have more entropy than those in the liquid state, which in turn have more entropy than those in the solid state. A pure solid at 0 degrees Kelvin has 0 entropy. This is by definition and/or the third law of thermodynamics. This concept can be applied not only to substances, but also the various forms of energy. For instance, work is an organized form of energy, and therefore can be converted into other forms. Heat is an unorganized form of energy, in other words, has high entropy, and therefore cannot be transformed easily into other forms. If we look at a cycle similar to the ones we saw in the past few videos, the integral of the change in heat over the temperature must be less than or equal to 0 over the entire cycle. This is equivalent to the Clausius statement we saw a few videos ago, and this has to be true for any cycle. If the cycle involves absolutely no irreversibilities and the entire process is reversible, then we should be able to analyze the reverse cycle and apply the same reasoning, meaning the integral must be less than or equal to 0 for both the forward and reverse cycles. The only way this is possible is if it is in fact equal to 0. So for reversible cycles, we get that this integral is equal to 0, as seen here. This leads to a formal mathematical definition of entropy, well, officially the change in entropy, ds, which is equal to the change in heat, delta Q, divided by the absolute temperature T, specifically for the reversible process. There's also entropy per unit mass, small s, or specific entropy. The change in entropy is then the integral of this quantity over the process, or delta S, which is S2 minus S1, is equal to the integral between states 1 and 2 of delta Q over T for the reversible process. Similar to energy, we don't really care about the actual value of the entropy. All we really care about are changes in entropy. The mathematical form of the definition of entropy, unfortunately, is not entirely useful. To actually evaluate the integral, we would have to know the functional relationship between the heat and the temperature, which is not always the case. In fact, it's hardly ever the case. So in most cases, we can calculate changes in entropy using data from tables. This is very similar to what we have done for the enthalpy, for instance, using water and tables A4, A5, A6, etc. You may have noticed those tables also have values of the entropy under the various conditions. One other thing to mention is that in the definition of entropy, there is a distinction that the integral will be taking for the reversible process. So even if the actual process that is occurring is irreversible, the integral is still evaluated using the reversible process. Remember that entropy is a state variable, just like energy. So the value of the entropy at each state does not actually depend on the path. And therefore, the change in entropy is also independent of the process. For example, this process down here corresponds to a change of entropy of 0.4 kilojoules per Kelvin. Regardless of whether it is the reversible or irreversible process taken to get from 1 to 2, the change in entropy is still the same. So, bit of a spoiler alert, what is going to happen now is to show that for any process to occur naturally, the entropy of the universe must increase. Hopefully this will make the following analysis a bit easier to follow. So I want to look at some process, really any process, that goes from state 1 to state 2. This could be either reversible or irreversible, and is shown by this dashed line, which is now purple. Now we know that for any process, that the integral of delta Q over T is less than or equal to 0. So for this process, we have this term here. But instead of just looking at that process, let's look at a cyclic process that consists of this first process followed by a fully internally reversible process, bringing us back to state 1. This is represented by this solid green line, which is now orange. Now we know for this term that it's equal to the change in entropy S2 minus S1, so that's this reversible one here. So moving terms around, we get that delta S must be greater than or equal to this integral from the first process, or using the derivative of this equation, ds is greater than or equal to delta Q over T. Similar to a previous discussion, this will actually be equal to 0 if the process is reversible. It will be greater than 0 for an irreversible process. So bottom line is that the entropy is generated during irreversible processes, and that overall entropy can never decrease. Note that this is for the overall entropy. The entropy of a system can actually decrease, but it must be in tandem with an equal or even higher increase of entropy of the surroundings, so that the overall entropy of the universe will always increase, or at least stay the same. So as a summary, the entropy of an isolated system will increase until it reaches a maximum value. Processes will only occur in directions that increase the entropy. Unlike energy, entropy is not a conserved quantity. For reversible processes, the change in entropy is 0. However, for any real process, there's always some form of inherent irreversibilities, and therefore the entropy increases in all real processes. This leads to a measure of effectiveness of real devices. The change in entropy will be the smallest for the process with the least amount of irreversibilities, and therefore these will be the most efficient. It was mentioned previously that the math is usually hard to actually do. However, there are some special cases where the analysis is made easier. The first case is any isothermal heat transfer. Keys here are that these are internally reversible and that the temperature remains constant. So the change in entropy is simply given by the heat added Q over the absolute temperature T. Another special case and a common scenario is pure substances. This is where we can make use of our tabular data to calculate the changes in entropy. This works the same as what we have been doing for specific volume, internal energy, enthalpy, and again should be familiar, like using tables A4, 5, 6, etc. Another special case are isentropic processes. An isentropic process is one in which the entropy does not change. Changes in entropy come from heat transfer or irreversibilities. So a process that is both adiabatic and reversible can be shown to also be isentropic. Many systems that we will be analyzing and are used in the real world can be approximated as isentropic. These include nozzles, pumps, turbines, etc. And because these processes minimize the irreversibilities, these can provide a baseline for the efficiency of real processes and/or devices. We have seen PV diagrams a lot. Another very common diagram is the TS diagram. These are very useful since the entropy, heat, and temperature are all related. If we rearrange the integrals a bit, we get this equation here, where the required heat for the reversible process is equal to the integral of TdS. In other words, the required heat is the area under the process in the TS diagram. And if the temperature is constant, then it's simply T times the change in entropy, delta S. Any isothermal process will be a horizontal line on the TS diagram. Any isentropic process will be a vertical line. Note that this will also correspond to no area and therefore no heat transfer. The TS diagram for water can be found in figure A9 in the textbook. There are also HS diagrams relating the enthalpy and entropy. These are useful for analyzing steady flow devices like turbines and nozzles, and can be seen in figure A10 for steam. So that is the end of the material for today. Here is your usual pre-lecture example. Bring any questions you have to class, and as usual, we will also see many examples of this.